In this video, we will be talking about the beginnings of limits, and we have two objectives. The first is to estimate limits using numeric or graphical approaches, and the second is to learn different ways that a limit can fail to exist. Before we get to that, there are some things we have to remember, and everything else that you see on the screen are just things that you have gone over in previous classes. So the first is the composition of functions, so f of g of x, or using different functions as inputs to another. The second are parent functions. So all of these functions we will be talking about later on during the course with limits, derivatives, integrals, but we will definitely start to use them with limits. I want to highlight one of them, and that is the rational function f of x is equal to 1 over x. Mainly because its denominator is x, so there is a value that it cannot be. So going back to domain and range, thinking about functions whose domain can't be certain values. So just keep that in the back of your head. And then besides that, transformation of functions. So we just went over this recently. Think about how these parent functions shift based off what we do with their output, their input, and their reflections. So what is a limit? If we picture a graph of some function, the limit as x approaches some value c of that function is the value on the trajectory of the graph at x is equal to c. So let's say, for example, that we have the function x cubed minus 1 divided by x minus 1. So before we even get to limits, I just want to think about this function as a whole. And the first thing I notice is that this denominator has a chance of being 0 when x is equal to 1. So x can't equal 1 on this graph. So there is no output for when x is equal to 1. And everything else, we could plug in different values of x, get out different values of y, and sketch the graph. And when we do that, we get this curve. And again, we should notice that at x is equal to 1, there is a missing piece. There is a hole in the graph. So if we wanted to find the limit as x approaches 1 of x cubed minus 1 divided by x minus 1, we would have to see what happens at that point on the graph. And in order to do that, we make a table of values and see what happens as we get closer and closer to x is equal to 1. So when we do that, we can plug in 0.75, we get out 2.31. Somewhere along this area. We can plug in 0.9 and get 2.71, 0.99, 2.97, and then we work from the other direction, right? So we can plug in 1.1 to get 3.31. We can plug 1.01, get 3.03. We can plug in 1.001, get 3.003. And as we get closer and closer to x is equal to 1, we get closer and closer to f of x equaling 3. So if this graph were to follow its normal trajectory, it would actually cross through 1, 3. So this limit is just equal to 3. So when we look at limits, we're really looking at what's happening on both ends of the point that we're talking about. And as we squeeze closer and closer to that point, that is the limit. So let's look at another example. So in this example, we have a function equaling to two things given certain x values. All right, so we have f of x is equal to 1 when x is not equal to 2. And we have f of x is equal to 0 when x does equal 2. All right, so if we just think about that, f of x will always equal 1 unless x is equal to 2, in which case it's 0. So our graph will look like a straight horizontal line for every x value that's not equal to 2. And when we get to 2, y will equal 0. And then it'll just continue on from there. So if we want to find the limit as x approaches 2 of f of x, we need to look at what's happening on both sides as we approach x is equal to 2. So again, we can look at this on a graph, or we can look at it numerically. All right, so for every value up until 2, so let's take x is equal to 0. When x is equal to 0, by this function, we know that f of x must equal 1. When x is equal to 1, f of x is also equal to 1, 1.9, and we could get infinitely close to x equals 2, and f of x would still be 1, except when x is actually 2, in which case it's just 0. But for every other value, it's always 1. Okay, so as we get closer and closer to 2 from each side, f of x will always be 1, so that actually is our limit. So the limit as x approaches 2 of f of x will just equal 1. And again, if we look at the graph that supports this, right? So if our graph were to just follow this trajectory, it would go through the point 2, 1. So again, limits are what happens as a graph approaches some value from both sides. But those values don't always have to exist. All right, so some limits just fail to exist because of a couple different reasons. The first is because the behavior differs from the left side and the right side. So for example, if we have the limit as x approaches 0 of the absolute value of x divided by x. Okay, so again, if we start to make a table of values, we can see what's happening on both sides of a particular value, in this case 0. So when we plug in -2, we would get -1. When we plug in -1, we also get -1. And when we plug in 0, we have our denominator equaling 0, which can't happen, right? So this is some undefined value. When we go to the right of 0, when we plug in 1, we would get +1, and when we plug in 2, we would again get +1. Right, so if we graph this, right, at 0, we don't have any value. To the right of 0, everything's always going to be y is equal to 1. And to the left of 0, everything will always be equal to -1. Okay, so if we just follow the graph, there is no particular value that's equal on both sides. Therefore, the limit does not exist. Okay, so the limit as x approaches c of a function doesn't exist if f of x approaches different values as x approaches some value c from both sides. So again, in this case, from the left-hand side, x is approaching -1, and from the right-hand side, x is approaching +1. So because those two things are different, the limit does not exist. Another reason a limit wouldn't exist is because of some unbounded behavior. So for example, if we have the limit as x approaches 0 of 1 over x squared, we know that at our value, the denominator is equal to 0, so we have some undefined value. All right, so what we do is we see what happens on both sides of that value. So again, we would go to our table of values, and we'd plug in different numbers. Okay, so when we plug in numbers from the left-hand side approaching 0, we'll see what the graph looks like, and we'll do the same thing on the right-hand side, and we'll try and get a value. Okay, so when x is equal to -1/2, we get 1 over negative 1/2 squared, which is equal to 1 over 1/4, which is 4. When we plug in negative 1/10, we get 1 over negative 1/10 squared, which is equal to 1 over 100, which is 100. Again, 0 is some undefined value, and then we work from the other side. So when we plug in positive 1/10, again we get 100. When we plug in positive 1/2, we get 4. And if we were to move closer and closer to 0, say if we were to plug in 1 over 25 instead of 1 over 10, our value gets bigger and bigger and bigger. So our graph looks something like this. And from both ends, we are approaching infinity as we go to 0. So as we get closer and closer to 0, our numbers get bigger and bigger and bigger, but we never actually reach a certain value. Therefore, our limit technically does not exist. Okay, so this limit as x approaches 0 of 1 over x squared, as of right now, doesn't exist. But we could also say that this limit approaches infinity. The third reason a limit wouldn't exist is because of some oscillating behavior. So for example, if we have the limit as x approaches 0 of sine of 1 over x, we get a graph that looks like this. And what's happening in this graph is as we approach 0, there are an infinite number of oscillations between 1 and negative 1. Okay, so this thick white part of the graph is actually an infinite number of peaks and minimums and maximums. Okay, so because as we approach 0, there is no fixed number 1 or negative 1, this limit does not exist. So to sum that up, there are 3 common types of behavior associated with the non-existence of a limit. Okay, the first is that the limit approaches 2 different values from the left and the right. So that's from our first example. The second is that the graph increases or decreases without bound as x approaches some number c. So that was our second example. And then the third is that our graph oscillates between 2 fixed values as x approaches some number c. Again, that was our third example. So to recap this entire video, there are really 2 main key concepts. The first is what a limit actually is. And a limit tells us what happens at a particular value based on the entire graph. Again, it's looking at what's happening at a particular point when you look at it from the left and from the right. Second is that they don't actually have to exist. So behavior could differ from left to right. There could be some unbounded behavior, or there could be some oscillating behavior at a certain point. So that is what we went over on this video, and that's all I have for you. Thank you for watching.